My dear friends, today I will discuss with you the basic difference between the quantity H and B. What is the basic difference between the two physical quantities? Remember one thing, what is H? What it is called? It is called magnetic field intensity. And what the B is called? B is known as magnetic flux density. Sometimes we confuse. It comes in our mind that H and B both are the magnetic fields. No. In SI units, in SI system, H and B, they are different. Their name are different. Remember what the name of H? Magnetic field intensity. What is the name of B? Magnetic flux density. Now coming first of all, what is H? And remember second thing, the unit of H. Okay, the unit of H is ampere per meter. Like for example, this is a coil having N turns. Current I is flowing through it. Now the coil will produce magnetic field intensity H. Okay, how much? H equals to N and I. What is N? Number of turns per unit length. Okay, mean that if there are N turns and the total length is capital L, then small n becomes N over L. And H also depends upon how much the current is flowing. So H depends upon N, H depends upon I. Okay, because it is a number of turns per unit length, so that's why the unit is ampere per meter. This first thing, H is Ni. Now second thing is, H is constant so long as N is constant, L is constant and I is constant. Okay, and is only affected from its origin. What is the origin? The coil, number of turns, length and I. Right? If these parameters are constant, then H remains constant. Now, on the other hand, what is B? The unit of B is Weber per meter square, or it is called Tesla. Now, you will ask me, then how the B is different from H? You know, when the current is passing and number of turns, then what it becomes? Small n means number of turns per unit length. Ni, so the coil generates coil, because of the coil it develops H, mean magnetic field intensity. But when the magnetic field intensity comes in the space in the coil or surrounding medium is the free space, or maybe it is a vacuum, then the vacuum or the free space interacts with the generated magnetic field intensity. And when it interacts, that becomes the B, magnetic flux density. So magnetic flux density is, you know what, B equals to mu naught H. Mean H originates from the coil itself because of the current passing. But when that H interacts with the surrounding medium, mean mu naught is what? Permeability of the free space, means surrounding space is free. Its permeability is mu naught. Okay, then BH changes to B because of the free space. Okay, the B becomes mu naught into the H. This is the difference between B and H. H is because of the coil itself and the current, and B is because of the interaction of the maybe free space or maybe the medium, and then it becomes the B. And the unit of B is different from the H because of the mu naught also having the units. Now the magnetic field B is a way of describing a region of space where other magnet will experience a force. You can define the B like this. Now H when interacts with the free space, that becomes the B. Now if you having some north pole here, having some magnet here, that will experience a force. Okay. So now this is a space surrounding the H. In that space, the magnet will experience a force. And the B, B is represented by the field lines. Like, if this is a coil, okay, and current is flowing from down to up, okay, then there will be field by the right hand thumb rule. The field will be along the axis like this, okay, that it becomes the north pole, it becomes the south pole, and there will be magnetic field around the coil. So long the current is passing, the coil turns into a magnet because of the current. Now the magnetic field strength H, magnetic field intensity I mean to say, when it is just generated by the coil, is nothing but the amount of the magnetic force, amount of the magnetizing force. So what's the role of the magnetizing force? The magnetizing force is directly proportional to current carried by the conductor and length of the conductor. I already told H is equals to like Ni. Okay, so this is a H, magnetic field intensity, and you can you keep in mind that it is like a magnetizing force. It magnetizes even the free. It tries to magnetize the free space even. Okay, because when mu naught is attached with the Ni, that becomes B. So this is the field in the space surrounding the coil, or within the coil, which is a space, it is having B, not the H. Okay, H is magnetizing force. It is magnetizing the free space or the vacuum, and then it turns to that field which is existing in the coil or surrounding surrounds the coil. That field is B. So B is nothing but the amount of magnetic force induced. So this is B is the force which is induced in any medium or in the free space. If there is any other medium, then you will say B equals to mu naught and Ni. For any other medium of permeability mu. Okay, so this is magnetizing force is H. It induced in the given body due to the magnetizing force H. The amount of magnetizing force induced depend upon the strength of H. So if this H is more, B will be more. And nature of the medium. And nature of medium means mu. Mu tells about what is the nature of medium, whether it accepts the magnetizing force, the action of magnetizing force or not. The mu contains that thing, whether it accepts or not. Okay, then becomes the P. Now, for example, we are having a magnet. Magnet produces a field H, but when H comes in the free space, it becomes B. Now, what is the role of B? Now, this is a paramagnetic material or ferromagnetic material. What is para or ferro? Ferro means there are certain dipole moments within the material. Like you can say ferro having some dipoles, magnetic dipoles, having some magnetic dipole moment within the material, but those magnets or magnetic moments are randomly oriented. Mean N is along this direction, this N is along this direction, this N is along this. So the magnetic moments is randomly oriented. But when we keep the magnet near this ferromagnet or the paramagnet, what happens? The dipole moment starts aligning themselves along the direction of the B. Okay. When it starts aligning along the direction of B, what happens? So this is our magnet. This is ferromagnet. Okay, this is the north pole of the magnet. You just see S, 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 S. Of all the dipole moments, it is towards the left hand side. And N, 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 N. It is towards the right hand side. So here develops N, here develops S. So this N, this ferromagnet is magnetized. It is magnetized now because of this magnetizing force B. B is magnetizing it. So it is iron or any ferromagnet. So it is magnetized now. When it is magnetized, it acquires the whole substance acquires some magnetic moment. Some magnetic moment means this phase acquires some pole strength. Let we call the pole strength as small m, and distance is L. Okay. So the pole strength M develops because of the P. So ferromagnetic substance material iron, cobalt, nickel. Okay. The molecular magnets mean these are the molecular magnets. Because of the external field, they are the alignment. This magnet transfers its magnetization to the iron. So now iron act like this iron, it act like a magnet of north pole this side and south pole this side. Okay, because magnetic moment, it is south to north. So this magnetic moment is along the direction of the magnetic moment of the magnet. Now what is the intensity of magnetization? Capital M. Capital M is, the definition is magnetic moment per unit volume. What is the magnetic moment? Okay. Now what is the intensity of magnetization? Capital M. Capital M is, the definition is magnetic moment per unit volume. What is the magnetic moment? Okay, what is the magnetic moment? Magnetic moment is, the pole strength M and the distance L. M into L is called magnetic moment. M into L. And what is the volume of this material? The area of cross section, this area of cross section, it is small a. Small a is area of cross section of this face multiplied by L, that becomes the volume. So magnetic moment is pole strength into distance. Volume is A into L. LL cancels out. So it left magnetic moment becomes M upon A. Pole strength per unit area of cross section. Okay. So that is, you know what it is, intensity of magnetization. And magnetic moment sometime, you know, it is if there is a loop, you know, and current is flowing along anti-clockwise direction. There's a loop, current is flowing anti-clockwise. Okay, the upper phase behaves like North Pole, lower phase behaves like South Pole. You remember like this N. Put the arrow. That means if the current is flowing anti-clockwise, that behaves like the North Pole. But if you see this same loop from the below, then the current is in clockwise direction. If current is clockwise direction, like you put arrow like this, complete it. And if current is clockwise, that is South Pole. From below it is clockwise, so below face is south, upper face is north. Now this is having the magnetic moment. What the magnetic moment is? Current into area. What is the current flowing and the area? The magnetic moment also, it is current into area divided by volume. So area and volume, you know, the units dimensions mean one dimension of length left in the denominator. The unit becomes ampere per meter, like here. It is ampere per meter. Magnetic moment having unit ampere meter square. Ampere meter square, volume meter cube. So it is ampere per meter. So this is intensity of magnetization. Now just see, if in the coil an iron rod is inserted, what happens? When there was no iron, okay, there was no iron rod, because of coil, the field intensity is H. But you know, if it is a free space, if it is a free space, it becomes mu naught H. Now mu naught H now interacts with this iron. This iron gets magnetized. When it gets magnetized, it also produces the magnetic field intensity. It is termed as intensity of magnetization M. M is induced by what? Mu naught H. Mu naught H induces M. Okay, and when M comes in the free space, the field of this iron becomes mu naught M. This was the magnetizing field which is interacting to iron. Iron gets magnetized and with magnetic field intensity M. But when that field comes in the free space, the field of iron, it becomes mu naught M. So total field becomes, total is now mu naught H, which was magnetizing to iron. And iron itself produces the field that is in the free space, that is mu naught M. So this is the total, mu naught H, which was magnetizing to iron. And iron itself produces the field that is in the free space, that is mu naught M. So this is the total. So total is, B equals to mu naught H, B equals to mu naught H plus mu naught M. Now next is, how much it is magnetized, mean M. M depends upon what was the magnetizing force H. So M depends upon, unit of M and H, they are the same. But M depends, the H depends, it is dependent on H. Replace the proportional sign by constant, that is chi. Chi is called susceptibility, magnetic susceptibility. So M is equals to chi into H. So this is the value of M, it depends upon H. This chi is called the magnetic susceptibility. What the relation becomes now? Now relation becomes B equals to mu naught H plus mu naught M. What is M? Mu naught H plus mu naught M is what? Chi M into H. Chi M into H. Right? Mu naught H taken as common. 1 plus chi M. Okay, this is B. Then now the B is also, if there is a material, H induces its effect in that material of permeability mu, and that becomes B simply. If I say this is iron, okay, iron is having permeability mu, H induces its effect. This is iron, okay, iron is having permeability mu, H induces its effect in the material, and that becomes then, a magnetic field develops, which is B equals to mu H. Now just compare the two values, this equation and this equation. Okay, that means mu becomes equals to mu naught 1 plus chi. This is a very important relation. Permeability of any substance is equals to permeability of the free space 1 plus chi m. Chi m is the susceptibility, how much the material having the acceptance for magnetization. Okay, thank you.